You are falling toward a black hole's edge. In 3 seconds, you cross a line where not even light escapes ever again. Stay with me, and you will learn what truly waits past that edge, and why physicists still argue about what fills the space inside. Here is the first surprise. Cross a supermassive black hole's horizon, and for one moment, you might genuinely feel nothing happen at all. So what exactly is that edge? Astronomers call it the event horizon, the precise boundary where a black hole's gravity becomes impossible to outrun. It is not a wall. It is pure math, the exact distance where escape speed must exceed light speed itself. Squeeze the whole Earth down to the size of a marble, about 9 millimeters wide, and it would finally become a black hole itself. But size changes everything. A stellar black hole, born from a dying star, packs several suns of mass into a horizon only kilometers wide. A supermassive black hole is stranger still. Cram 4 million suns into one horizon, and the average density can be thinner than ordinary air. That is not a typo. Bigger, in this case, means gentler. Exactly why subscribing now means you will not miss what comes next. So which black hole would you rather fall into? The violent small one, or the deceptively calm giant sleeping at our galaxy's center? Either way, gravity eventually wins. Tidal forces stretch you lengthwise and squeeze you sideways, a process physicists actually call spaghettification. Near a small stellar black hole, spaghettification starts brutally early, tearing you apart well before you ever reach the horizon itself. Near a supermassive black hole, tides are gentle enough that you could cross the horizon fully intact and never notice the moment it happened. But that mercy does not last. Deeper inside, the same stretching force returns, and this time there is no boundary left to save you. Therefore, everything falling in, light, matter, information itself, is dragged toward one point, the singularity, where our equations simply stop working. Here is the strangest part. Physicists now argue the singularity is not a place at all. It is a moment in your own future. Inside the horizon, space and time effectively swap roles. You cannot dodge the singularity any more than you can dodge tomorrow morning. But general relativity, the theory predicting all of this, was never built to describe something infinitely small, so a deeper theory must take over. Some physicists doubt a calm crossing. In 2012, a team proposed something far more violent waiting at the edge. They called it the firewall, a wall of lethal radiation sitting exactly at the horizon, burning away anything that ever tries to pass through. If the firewall is real, Einstein was wrong. Falling in would feel like fire, not nothing. Other physicists reject firewalls entirely. String theory offers a stranger fix, nicknamed the fuzzball. No true horizon and no interior at all. A fuzzball is one tangled ball of quantum strings reaching almost to the horizon, radiating faintly like a strange exotic star. Three rival pictures now compete for one black hole, a singularity, a firewall, or a fuzzy ball with no inside. In 1974, Stephen Hawking found a fourth twist. Black holes are not perfectly black. They leak a faint mist of particles. Hawking's math implied the radiation carries no information. Everything could be erased. Quantum physics forbids it. In 2020, a new calculation called the island formula tracked the missing information, suggesting it escapes, encoded in the outgoing radiation. Past the edge, the honest answer, nothing is destroyed. It is scrambled, held, and returned, transformed. Every telescope image we own, including 2022's picture of our galaxy's black hole, shows only a shadow, never the inside. The true interior remains the last locked room in physics. Subscribe and join us as scientists race to finally pick that lock.